just we're going to talk about working some limit problems today. When we work limit problems, we have to remember a lot of different things. First of all, is it approaching C? And if it is, do we get L infinity or negative infinity? Is x approaching infinity? And do we get L infinity or negative infinity? And is the limit of f of x as x approaches negative infinity, do we get L infinity or negative infinity? Here we have some one-sided limit definitions. As we approach c to the right and c to the left, where we may get infinity or negative infinity. So we have a lot of considerations to do. Another consideration we have to do is what happens as x approaches infinity. That gives you a whole new ball game. Maybe you get a number L, but you could get infinity or negative infinity by looking at the degree and comparison of the degree of the numerator and the denominator. Now remember, at this point, I have considered that you have read and listened to all my videos. So when I'm picking problems here, I'm picking the good stuff. So as I look in my book and I go through all the problems we did in 1.2 and try to analyze what limit problems you should have had or not had trouble with, I come across that I'm not going to prove this, I'm just going to talk about this, is did you have a problem with if you did substitution? For example, can everybody take the limit as x approaches 4 of x plus 1 over x minus 3? Okay, nothing's undefined. Your answer is 5 over 1. So this would fit the limit of f of x as x approaches c as L. We come across something, however, that may look like this. What about the limit of the square root of x plus 5 minus 3 over x minus 4 as x approaches 4? Entirely different ball game here, because if you put a 4 in, you get a 0. If you put a 4 in here, you get the square root of 9 minus 3 is 0. So that's big time. And we're not in chapter 2 where we can do it by one single step. So if you remember here from previous videos, all I did was I rationalized the numerator with the conjugate. So the top, you have to always repeat limit each time. The top gives you f plus 5 minus 9, and you leave the bottom in 2 terms. So the top will give you x minus 4. So the culprit will cancel out. You would discontinuous it at 4, so x equals 4 is a removable discontinuity. See what a good review this is? So you canceled it out, they gave you a 1 at the top. You put a 4 at the bottom, you'll have 6. So your answer to this limit is a sixth. I am now glancing over 1.2, and I think that covers it. When I change the page, if it does change, I'm in 1.3. It goes through factoring, rationalizing, and at this point, I'm leaving out the squeeze theorem till we can have time to discuss it on Tuesday. You can find the proof, however, for your viewing enjoyment, of the limit as x approaches 0 of the sine of x over x is equal to 1. And if you don't want to use x, theta approaches 0 is my favorite, of the sine of theta over theta. And you can then extend that to be the limit of theta over sine of theta as theta approaches 0 is equal to 1. In a handout I've already loaded up called Limit Supplements. You have it activated on your website. You have to search for it, and it's going to say proof using squeeze theorem. Very, very good bedtime reading. Now, as I go through all of this, I see that we took and talked about taking all the special 6 limits. I asked you in one of the sections of the website to go and analyze all 6 by exploring with a graphing calculator. The reason this is necessary, as I told you in a previous video, is that you have to memorize it. If you ever forget them, you can use the graphing calculator. Now, y'all have to remember something here. Today in the hall, when I was asked, well, what is the limit of the cosine of 1 over x as x approaches 0? I took, and I tried not to let the child see that I was a little bit aggravated. No, I was a big bit aggravated about that question, because I knew he hadn't looked at the website, I knew he hadn't read the book, and I knew he hadn't watched the video. That was one of the special limits I asked you to explore through the graphing calculator. That answer does not exist. The reason being is 1 over 0 is undefined. The cosine of undefined is what? Doesn't exist. Contrary to this, and you can explore this with the graphing calculator, when you multiply it by x, you have an interesting thing. This is going to oscillate, and as it gets to 0, you're going to have this crazy graph going like this, and up and down, and up and down, and up and down. Look at your table. But when it does, you're multiplying it by 0, and that's why this answer is 0. So you need to pay very, very attention to the special limits. And in doing so, page 3, come on, baby. On page 3, that puts us in 1.3. And when I look at these problems, just taking a look at some of them, I'll go to 61, and it says the limit of the secant of 2x as x approaches 0. You better know your graphs, because the secant of 0 is 1. There are 6 trig graphs. They're not 3. You never, ever see me when I say graph a sine, take my graph paper and then do cosecant on the same graph. All 6 trig functions have special properties. So if I look at a cosecant graph and it's like this, at pi over 2 it's 1. Then it's like this with vertical asymptotes at 0 at pi, and it comes down here, and then it comes here, and I'm talking about y is equal to the cosecant of x, and this is x equals 2 pi. You know what's in my head may not be what's in your head, but what's in my head is I say to myself, self, the limit of the cosecant of x, as x approaches 0 from the right-hand side is a positive infinity because Josie knows her graphs. The limit of the cosecant of x as x approaches pi from the left side is a positive infinity. And then I see as x approaches 2 pi from the left side, it's a negative infinity, but this sets aside my graph. It tells me it's 0 to the right, I'm at infinity, to the left, I'm at infinity also, and x approaches pi to the right, I would be at negative infinity, and at 2 pi to the left, I would be negative infinity, because I know my graphs. I know that the fundamental period of a cosecant is 2 pi. I know that fundamental period of a tangent graph is pi units. I know that in y is equal to the tangent of x, that my graph has asymptotes at pi over 2 and negative pi over 2, and that is what it looks like. It's a story of limits. So, can I give you good advice on this? And I kind of feel sad about saying it because this is your first week of school and you want to be home on vacation, and then we give you a little vacation called Labor Day. And so as a result, you still think you're on vacation, but you're not. There are 6 trig graphs. You have a grade in pre-cal. You didn't take your final. Missed a good one. You need to know the 6 trig graphs and their periods. I suggest you take out my notes from pre-cal or Ms. Zorn's, but I think of everything in terms of 6, not 3. Remember that. A little while, next chapter, I'm going to tell you that there are 6 inverse trig graphs. You need to know them and their periods. So heads up. Okay, so as I look at 1.3 and I search for problems you need to use, all I see is that they ask a lot about trig functions. That means you need to know your graphs. In the problems that they have your special facts, then which ones have I not worked for you? Let's look at 78 for special limits, and it's a limit as x approaches 0 of the sine of 2x over the sine of 3x, remembering well that I've worked this for you. Remember, it comes from the limit of the sine of theta over theta as theta approaches 0. I've worked this before, but it's worth it again. Since this is a 0 over 0 and you don't know chapter 2 yet, you're going to have to rig it. So this is an angle. This is an angle. So put the angle here. But you sinned, so you have to repent. For the sine of 3x, it was on the bottom. This is the angle. There's no angle here. So sin and repent. So you have the sine of 2x over 2x is 1. You have a 2f left over. 3x over the sine of 3x is 1. 2x over 3x. So the limit of 2x over 3x, because of the property of cancellation, is 2/3. So that's the only thing interesting in 1.3. You, however, are going to be working these assignments, and you're going to find a lot of interesting things that you're going to ask questions about on Tuesday. And I can't wait to see you again. Okay, so we search and we search and we search, and we come to section 1.5, and they talk about vertical asymptotes. Well, you have a vertical asymptote when what? You have a vertical asymptote if we have a rational function if y is equal to f of x over g of x, a vertical asymptote occurs when g of x is equal to 0. I'm turning the page, and that's the noise you're hearing, and I'm looking for problems of 1.5. So I'm going to change my pen. I've said all the important stuff. So let's change the color again to basic black, and away we go. So only thing we have to consider is this. If you are now going to x approaches infinity, and you have a problem where you're considering the limit of 2 plus x over x squared times 1 minus x, you're considering a situation, and this really is negative x cubed plus x squared. You're considering a situation where the degree of the numerator is 1 and the degree of the denominator is 3. So this outdoes there, so your answer is 0. Now, I want to now do it, since you're so much more mature, I want to do it in terms of the theory. So if you give me a minute, I'm going to reinterpret the problem. What works every single time, no matter how complicated the problems are, and if x is going to either infinity or negative infinity, it works both times, is you factor out the highest degree in the top and the bottom. So for that problem, I'd rewrite it. If I'm doing theory, I take an x to the first out. This gives me 2 over x plus 1. Remember, it has to check back. So x times 2 over x is 2, x times 1 is x. The highest degree here of negative x cubed plus x squared is obviously x squared. So that's already factored out. And you have 1 minus x. So now you play with your head. You say to yourself, self, as an x over an x squared, when it factors out, will give me just an x on the bottom. As x goes to infinity, 2 over big guy will be 0. 0 plus 1 is 1. Go to the bottom. You have an x left here. As x goes to infinity, you have infinity, more larger quantity. So the quantity here gets very large. Therefore, the answer is 0. Now, this theory of factoring out the highest degree of the top and the bottom is very, very relevant when our problems become harder, and I'm waiting for you to ask that good question. One of you have already done so and figured it out because I just kept my mouth shut and watched him do it. Okay, suppose you have the limit as x goes to infinity of negative 4x over x cubed plus 4. Okay, if we use that procedure, you would just say, well, the highest power is in the bottom, so my answer is 0. Now let's do the theory. I want to do the theory just so to be sure that you're cool. You factor out the highest degree at the top. You factor out the highest degree at the bottom. Okay, now I'm cool. Except I took out an x cubed, so this is an x cubed, Josie. Negative 4x, and this is x cubed plus 4. This factors out and reduces to x squared on the bottom. So you are left with a negative 4 at the top, and at the bottom you have x squared. As x goes to infinity, 4 over big is going to be a big fat 0. 1 plus 0 is 1. 1 times x squared is truly big, so negative 4 over big guy is going to equal 0. I'm trying to let you see how the factoring works. Now, I'm going to pause for a bit because I'm going to go get your sheet on your graphing that you did on the very first thing I turned to you, because I want to see if I have better problems than in the book. So excuse me for a second while I go get my homework. Okay, I'm back. I have your packet. I'm in your homework of finding limits algebraically, and I'm doing the problem that is number 35, and this is on the graphing sheet. I'm doing the limit as x approaches infinity, is what it looks like to me, of 4x cubed, nope, 4x to the fourth, over 6x cubed minus 19. Okay, the top's bigger. Both leading coefficients are positive, so that means it's infinity. Now, let's prove it by that theorem of factoring out the highest power of the top and bottom. As x goes to infinity, 19 over x cubed is going to be 0. X cubed and x to the fourth leave you an x. So you have the limit as x goes to infinity of 4x over 6. So this indeed is a big top. Now, 37 is cute. Okay, now put your thinking cap on and try to follow. You got a square root. You don't know what you're going to do with it. Well, that's when you do theory. You factor out the highest degree in the top. Well, guess what? It's itself. Now, in the bottom, this is x going to infinity. In the bottom, you would have an x squared times 1 plus 4 over x squared under a radical. So this would give you the limit as x goes to infinity. Now, pay attention. You have an x at the top. Let's get this out of the way. The square root of x squared is the absolute value of x. More time. The square root of x squared, algebra 1, is the absolute value of x. You determine its sign by looking at where x is going. It's going to infinity, so it's going to be a positive x times the square root of 1 plus 4 over x squared. This will cancel with this. As x goes to infinity, 1 plus 4 over x squared is 4 over big. 4 over big will give you 0. So your answer is 1. Now, I want to do this problem again and change it up. Suppose I have the limit as x goes to negative infinity of x over the square root of x squared plus 4. In theory, the top would stay as an x, because I'm not doing anything to it. But when I take, and I'm on this step right here, when I factor this out and I have the square root of x squared, I would have to interpret it as a negative x because x is going to negative infinity. So as x gets big, this is 0, so I have my 1. This would cancel with this, so my answer would be negative 1. Now, so you won't get so mixed up when you try to look at this with a pen, I'm going to do the old pen trick. So this problem went choo-choo across the top, and concluded here. Trying to show you differences, canceling out the x's here. This was the second problem at the bottom. So this concludes 1.2, 1.3, 1.5 in the text, your special limits exploration, and the graphs and the algebraic interpretation in your packet. You say, okay, I've done the definition of limits. I've done all that. I don't have a life. All I'm doing is calculus. Isn't it fun? So when you get back, we are going to first be able to take up homework. My grade speed isn't fixed yet, so I can't do it. Number 2, we're going to explore 1.4. And if you look down the context box, you see limit supplements and you see pretest on limits. You're going to be pretested so much. I don't know how you're going to help, but break the curve on your test. Love you and good night.